Now this is our slope vector equation, or if you were to put these three things into the components of a vector, you'd get your slope vector equation, where as you change t, you'll get different values of your slope vector. We are only looking for the slope vector of t equals 2. Now, just quick clarification, when I say slope vector, I'm essentially saying slope of the tangent line. But once again, because slope is no longer just like rise over run, it has to be represented as a vector, I'm calling that vector the slope vector. So, t equals 2, you end up with your slope vector at t equals 2 being 3 times 2 squared, which is 12, plus 1, 13. 4 times 2, 8. And 2 times 2 plus 1, 5. That's your slope vector. Now we still have to do the y equals mx plus b part, the like adding or just making it a whole equation. So we take the components. Your slope of your x component is 13. 13 times t plus b1. For the y component, 8t plus b2. And z, 5t plus b3. How do we find b1, b2, b3? Obviously, like we can't just leave it like that. We need to finish the equation. How do we find b1, b2, b3? I'm going to quickly rewrite our initial curve. X equals t cubed plus t plus 5. Y equals 2t squared plus 2. And z equals t squared plus 2. Oh, plus t, my bad. All we want to make sure this tangent line does is it has to touch the point that we're taking the tangent line of. So say this is like the curve, and this is at t equals 2. This tangent line has to touch the curve at t equals 2 to make it a tangent line. That means that this curve just has to have a point. This tangent line has to have a point that is equal to the point on the curve. And how would we find that? Well, I think the easiest way is to say that this tangent line touches this point on the curve at t equals 0 for this. Remember, this t does not necessarily have to equal that t. They're just parametric like values. They really don't have anything to do with each other. So let's say for the tangent line we reduce t to 0. That'll leave us with x equals b1, y equals b2, and z equals b3. Now all this means is that we're taking this tangent line and we're isolating to one point at t, where that point is at t equals 0. And you're left with the coordinates b1, b2, b3. Now, to ensure that this tangent line touches our curve, all we have to do is say that b1, b2, b3 are like coordinates on the tangent line, on the curve when the curve is at t equals 2. So, b1 is the x coordinate of the curve at t equals 2, b2 is the y coordinate of the curve at t equals 2, and b3 is the x, did I just say x coordinate 3 times? Let me re-explain that. b1 is the x coordinate of the curve at t equals 2, b2 is the y coordinate of the curve at t equals 2, and b3 is the z coordinate of the curve at t equals 2. All you do is plug in t equals 2 to the initial curve, and you get x would be 2 cubed, which is 8, plus 2, which is 10, so 15. T2 squared is 8, T2, okay, I did not say that right, but anyway, that would be 10. Then 4 plus 2 is 6. So b1 is 15, b2 is 10, and b3 is 6. So you end up with your final equation being 13t plus 15, 8t plus 10, and 5t plus 6. Now, I really hope that this was informative and this explained everything you had to know about tangent line equations. And I hope that this kind of way of explaining it with these slope vectors, which is what I like to call them, was like informative. It's the way I think about it, and I think it's very helpful to me and some of the other people I've explained this to. So I hope that was good. Obviously, I could have just shown you the process, but I really hope this was like insightful on what's really going on. And I'm gonna go watch that Percy Jackson episode. Goodbye. How long was this? 23 minutes? Oh my god, there's gonna be in like so many parts. Yep, have fun.